This conference will now be recorded.
Hello, everybody. Welcome to the Satellite Book Club Seminar Series. This is session number 62. Thanks for being with us today. Hope your summer is going well. Today's presentation is the CIMSS GOES-16 17 Turbulence Probability product, CruiseNet version 2, a CWSU's perspective with some examples. Our presenter today, Sean Campbell, meteorologist from the Washington Air Route Traffic Control Center, CWSU ZDC. Our facilitator is Tony Wimmers, Associate Scientist with the Cooperative Institute for Meteorological Satellite Studies. Just a few reminders before we get started today, that as you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation, so please post your questions in the chat room and we will field them in the order they are asked. We're always looking for future presenters, particularly from our field offices, so if you have an application you'd like to share with your colleagues, please get in touch with us. And the training team can help create training materials that may be unavailable or point you to materials that you may be unaware of. And Brian Mata, the Office of the Chief Learning Officer, can help with that. I'd just like to thank the Tower S team, particularly today we got Lee Byerly stepping in for Kashad Bowman, the Office of the Chief Learning Officer, the GOES-R, and the JPSS program. Thanks to all of you for being here as well. Without further ado, I'd like to introduce Sean Campbell at the NWS Center Weather Service Unit. He's a meteorologist. Before joining the National Weather Service, he served as a weather officer in the United States Air Force for 10 years. He earned his bachelor's and master's in atmospheric sciences from Creighton University. Sean, welcome to the book club.
Well, thanks for having me. Again, I am Sean Campbell. So today I'm going to be presenting on the CIMSS GOES-16 17 Turbulence Probability product, also known as the CruiseNet version 2 product. So my presentation is going to be a Central Weather Services Unit perspective on this with examples. And we're lucky enough to have the facilitator as Tony Wimmers, who is actually the developer of this particular product. So a brief overview, I'll talk a little bit about Central Weather Service units, then I'll talk a little bit about Washington Air Route Traffic Control Center's airspace, some turbulence and convection impacts in ZDC's airspace. Then I'll give a brief description of the CIMSS GOES-16 17 Turbulence Probability product. And then we'll get into the meat of it, which is going to be several examples from May to July of 2021, again, of the CIMSS GOES-16 17 Turbulence product and how it performed in certain scenarios. And then I'll wrap it up. So CWSUs essentially monitor and provide weather forecast advisory and briefing support to the nation's 21 air route traffic control centers, and their airspaces are shown on this map that we see here. There generally are 4 meteorologists at each of these CWSUs. So essentially what we do is we provide IDSS, or impact-based decision support services, to the FAA, to the ARTCCs, which are Air Route Traffic Control Centers, and then to any of the other offices FAA-wise that would be within or fall under the jurisdiction of these particular ARTCC airspaces. Washington Air Route Traffic Control Center, ZDC's airspace is very complex. It covers approximately 165,000 square miles. It's very high volume. It sequences and separates aircraft to and from about 21 of the nation's 50 busiest airports. We have presidential support that we have to pay attention to. We have vast areas of airspace dedicated to military ops, and sometimes that military operational airspace is offshore and it can be shut down. So that actually cuts the amount of airspace that we have to use to have traffic flow through ZDC. So that presents a big challenge as well. There are 46 operation sectors within ZDC, which are stratified by different altitudes and organized in 6 areas of specialization, which we can see here. Areas 1, 2, 3, 4, 5, and 6. And the sectors are designed based on traffic flows, so arrivals, departures, and overflights through and across the Mid-Atlantic region. Majority of ZDC's air traffic is arrivals and departures, but there's still quite a bit of traffic that actually flows in route-wise, so between about 30 and 41,000 feet through ZDC's airspace. So one of the big sectors that we have to pay attention to is the airspace that flows northeastward through Philadelphia on into New York, Boston, and then internationally. And within that, we also have DC and Baltimore, we have Richmond, and we have Norfolk. And then to the southwest, we have airflow to the big airports of Atlanta and Charlotte. And then directly to the south, we have pathways or airflow to Orlando, to Fort Lauderdale, to Miami, down to the Caribbean. And then to the northwest, the big airports that are serviced from ZDC would be Chicago, Detroit, and Cleveland. And again, we also have some ZDC North overflights. All these are color-coded, and they are flying to these specific airports. So EWR, LaGuardia, JFK, Newark, that is, Philadelphia, and Boston, they all flow through ZDC airspace. So as you can see, it's a very complex airspace. So areas of moderate or greater turbulence and convection can really cause some issues and can cause ZDC's traffic management unit to do a number of things, not list or not. I know some of those would be required. They would require increased spacing between aircraft along a certain route. They would require aircraft to fly at different altitudes than they would normally fly at. They would shut down air traffic routes, and they would reroute traffic. And these are just a few of some of the actions that they could take to try to avoid some of this moderate or greater turbulence and convection. As a result, any action that they take can strain the national airspace system. So monitoring satellite imagery for turbulence and convective signatures is really a vital piece of what we do in ZDC at the CWSU. Satellite products such as the CIMSS GOES-16 and 17 Turbulence Probability product can really help us diagnose potential problem areas for en route flights. Since about November of 2020, we at ZDC CWSU have been actively using and evaluating the CIMSS GOES-16 and 17 Turbulence Probability product and providing feedback to the developers. I wanted to make everyone aware that all the examples in this presentation have been shared with the developers, so they're not going to get blindsided by anything that I'm going to be talking about today. So what is the CIMSS GOES-16, 17 Turbulence Probability product? Well, it was developed by Dr. Tony Wimmers, who again is the facilitator today, and his team at the Cooperative Institute for Meteorological Satellite Studies, so CIMSS. It had some images and loops showing a probability of moderate or greater turbulence over a 10-minute flight segment through an area. And these images and loops are created using machine learning. So what goes into this is thousands of turbulent and non-turbulent cases, which again are used to relate satellite structures to create the predictive model between 30,000 feet and 41,000 feet, which is the cruising altitude for most commercial aircraft. Some of the GOES-16 and 17 bands used in both the model and its underlying displays on the resulting product include the ABI band 8, which is water vapor imagery, and the ABI band 13, which is the clean window IR. And for all of the examples that I'll be showing today, the underlying display is going to be the water vapor imagery. For more information about the product, you can either visit the Turbulence Probability Quick Guide, which I've shown here, or the website. As a caveat, it is actually available on AWIPS, but only right now in the 36 to 37,000 foot layer at the time of this presentation. Again, contact the Tower S team for more information about this, as they've been able to work with Steve Zubrick, who's our SU at LWX for WFO Sterling, to get this piped into our AWIPS remote display at the CWSU. So when you first pull up CIMSS probability product on the website, this is what the product really looks like. A couple things to point out there. Note the contour percentages and how the turbulence higher-ups are displayed. So I've got that highlighted in blue here. So the probability of moderate or greater turbulence starts at a contour interval of 10%. That's in blue. And then there's a darker blue slash, I guess you would call it dark blue slash green at 20%, and then 33% in green, and then 50% or greater probability of moderate or greater turbulence in yellow. That's the yellow contour. And then the PIREPs are all shown right below that. There are many choices once you get to this website main page there. You can choose different satellites. You can choose different times. The date and time goes back 48 hours, if I remember that correctly. You can choose the Northern Hemisphere there. The view method is either a single image time or you can do a loop. And there are many different regions that you can choose from as well. And there are a couple of different parameters you can choose. Really what happens when you click on this is you either get the underlying image of the IR imagery or the water vapor imagery. And then there are levels there. So it goes again from 30 to 41,000 feet in 2,000 foot intervals or increments. And then there's also a maximum percentage within the 30 to 41,000 foot layer. And most of what I'm going to be showing in my examples are the 30 to 41,000 foot maximum, because I find that's a good way to kind of pinpoint some of those areas that might have potentially more turbulence issues than some of the other areas. I will say that the last example that I showed just is basically a 36 to 37,000 foot layer example. Okay, so getting into some of the examples, we've had a couple of tropical systems that have impacted the eastern half or so of the United States in the last couple of months. The first one was Tropical Storm Claudette that I was able to capture. And as you see in the image on the left there, I've got the 30 to 41,000 kilofoot or 30 to 41,000 foot maximum. And you can see it did a really good job of highlighting some of the turbulence impacts associated with the convection with Claudette. Where it might not have highlighted quite as much turbulence as one might expect would be kind of around the periphery there. And you can see in some of the images on the right, we did have a bit of divergence in the upper levels there. So that's just one example where it might not have shown perhaps enough turbulence or that we might have expected. You can see that there's also some wave action in the satellite imagery there, which we see on the left. Another one with Tropical Storm Claudette, which was which was the next day. This is as Claudette was moving a little bit farther inland and beginning to interact with some of the westerly flow that was across northern portions of, or at least central portions of the United States. And you can see it did a pretty good job of highlighting at least areas or the potential for some turbulence, again, within that 10 to 15 minute interval that I talked about earlier. And it, again, did a really good job there. You can see it's got a lot of at least 10 to 20 to maybe 33% probability of detection across the area where there was quite a bit of moderate turbulence highlighted there. So looking at what was actually going on at 300 hectopascals there is, again, we had Tropical Storm Claudette moving inland and interacting with some of the westerly flow there, and there was some embedded areas of divergence. Tropical Storm Elsa, these next four slides are going to be all about Tropical Storm Elsa. So starting on July 7th in the morning there, you can see it did a really good job highlighting areas of moderate or greater turbulence right within the area of convection associated with Tropical Storm Elsa. At the same time, there's quite a bit of diffluent flow, so that may have helped cause some of that turbulence that the predictive model was looking at there to highlight some of those areas of turbulence there. There's one little area that is just outside of that west of that area where there's just a little bit of turbulence, moderate or greater turbulence detected. That's actually just kind of on the east side of a weak upper level low there. And then moving ahead there in time on July 8th, during the overnight hours there, again, more really good turbulence detection, at least 33% in these areas where the moderate or greater turbulence between 30 and 41,000 feet was detected. You can infer that on the satellite, there was quite a bit of convection across that region, and there was also quite a bit of divergence within that area where the turbulence was detected. Moving ahead in time, as Tropical Storm Elsa continued to move up the coast, again, good detection right within the convection or the core of convection associated with Tropical Storm Elsa across southeastern Virginia, also where we had an area of upper level divergence. And then there's one area, up there in Pennsylvania, where we had an area of severe turbulence, or at least one report of severe turbulence at 33,000 feet. That too looks like it was in southwesterly flow with a little bit of divergence up there. And the product actually did a pretty good job of highlighting at least the potential for some moderate or greater turbulence right in through that region. So I'd call that a pretty good forecast there. And then moving ahead to July 9th in the morning there, quite a bit of turbulence was reported in the New England region. And there was a lot of dynamics going on with that on that particular day. We had a lot of divergence and diffluence aloft. And then we also had this whole area up here across eastern New York and extending into Massachusetts and Connecticut. It looked like that was also at least partially within the right entrance quadrant of a pretty strong jet max there, jet maximum. So there was probably some upward vertical motion as well within that region, which is helping to mix things up a little bit. And you can see all the waves that were being detected on the satellite as well. So again, another good case where the product detected quite a bit of turbulence. And then we'll get into some more sharp upper level trough. These next three slides are going to be all about a sharp upper level trough that moved across the Great Lakes region on July 8th. In this particular case, you can see how sharp that trough was. There was a really strong jet max that was starting to punch into the backside of that. And then we also had a lot of areas of divergence, which we can see in yellow in the center portion on the bottom center image there. So quite a bit of turbulence all within that 30 to 40,000 foot layer there, it looks like. And I just wanted to point out, I also threw some SKUTs into this one. So what I'm looking at here is we did have some areas where we had some inversions towards the top of that 30 to 41,000 foot layer there. So that might have helped trap some of the waves and cause more of that turbulence that was being detected very well again by the product. Same thing, this is just a couple of hours ahead of that. Oops. Again, you can see that very sharp trough. A lot of jet dynamics associated with that on the backside and also on the eastern side of that. A lot of divergence as well. So that whole area was highlighted very well. Again, we can see a large area where greater than 50% probability was detected. And that kind of nailed it, I would say, on this particular example. And we can see the trough beginning to flatten out a little bit by 1740 UTC on July 8th. But again, still a broad area of very good detection, it looks like, on this particular map here. Again, the CIMSS GOES-16, 17 probability product did a very good job, I would say, with this trough detecting turbulence as it continued to push eastward through this entire time frame. And then a few other features. On May 4th, we had a very strong jet max that was kind of moving from southwest to northeast. There's a lot of jet dynamics associated with that. And again, very good detection. It looks like within the entire 30 to 41,000 foot layer. Looks like the top to this hit about 37,000 feet in terms of the moderate turbulence. But this whole area that is right within that strongest area of jet stream shear was detected very well by the CIMSS GOES-16, 17 turbulence probability product. Another one on May 15th. This one didn't do quite as well in terms of detecting turbulence, but this is one of those cases where there wasn't really a lot of shear associated with this particular scenario. It might have been more that there was some wave action towards the tropopause, because as we can see on some of the SKUTs to the right here, the Nashville SKUT does show a very strong inversion right around 40,000 feet or so, 200 HPA, and then much the same at Peachtree City, Georgia. And this whole area is where that moderate turbulence was being detected there. So there probably was a little bit of wave action right along that and below that tropopause layer. That's what was causing the turbulence there that the predictive model might not have picked up too much on. On May 16th, during the afternoon hours, we had another pretty good detection by the CIMSS GOES-16 turbulence probability product. We had a lot of jet stream shear associated with this particular case. And again, a lot of good detection right within that area there, and even one severe turbulence. It's kind of like right on the edge or the gradient of where we were seeing some of that turbulence being predicted there. So again, good there. Maybe not quite as good just outside of that, southwest of there. But again, that was one of those cases where we had outside of that, there just wasn't a lot of shear associated with this one. So there might have again been some waves that were kind of riding just below the tropopause there. And then here's the case on July 9th, where the detection wasn't quite as good. And what was going on here, it looks like there was some pretty decent convection that had fired across Iowa there. So there might have been some input from all that convection in the upper levels that might have flowed outside of where the turbulence was being detected there. So again, there was a lot of turbulence right within this region that wasn't really being detected. That fell within a broad upper level trough. And again, there was actually quite a bit of divergent flow within that as well. So there might have been a little bit, there were some other reasons that might have caused some of this turbulence, and some of the predictive model might not have picked up on some of that. And then the final one that I have is one in which we had a severe turbulence report that actually was outside of the convection. And the meteorologist on duty said that he was really impressed with the turbulence probabilities product to pick up on that area, as it alerted him to the potential for that moderate or greater turbulence that was just outside, of that convection. And that was just kind of on the nose of a jet max that was kind of punching southeastward there, right into that general region. So as a wrap up, some takeaways include we've seen significant improvements in the CIMSS GOES-16-17 turbulence probabilities product ability to detect moderate or greater turbulence since late 2020. The product does detect moderate or greater turbulence well in several situations, such as dynamic environments like sharp or strong upper level troughs, strong jet stream shear, near jet maxima, in strong convection, close to tropical systems. And the product may not detect moderate or greater turbulence quite as well in a few scenarios, but it'll probably detect at least some moderate or greater turbulence potential, that is, in the outskirts of tropical systems, particularly weak ones, areas of weak shear and stratified flow, and downstream waves, gravity waves, whatever they might be, whatever type of waves they might be, enhancement from upstream convection and otherwise weak flow. And evaluation at the CWSU level continues. And whoops, I will take some questions now. Thanks again for the opportunity to share research and evaluations.
Thank you, Sean. This is Tony Wimmers. I'm told to step in now and as the role as facilitator. First of all, Sean, thank you so much for this. We really benefit a lot from your good in-depth evaluations of this product. It really helps with the development cycle of this. And I'm sure it also goes a long way to lead the effort in getting other people to understand the right way to interpret this. So we're really grateful for that. So I have a few housekeeping remarks, a few notes. One is please share any feedback you have on this session or the SBC in general in a short survey. That is going to be shown in a slide that Lee will bring up. And also, as we know, many of you are very time constrained. You can recognize this half-hour mark as a time to go back to duties, but you are very welcome to come in, to stay as long as you like for discussion. And that discussion is either posting comments in the chat or making some sign to give a live question. Also, please join us Thursday, this time next week, for Dr. Katie Crandall Vigil from the other CIMSS and NWS-OPG to present color vision deficiency and interpreting satellite RGBs, current research and future opportunities. And if you need assistance with the configuration of satellite products, that includes what you saw this week, but is not limited to that. The Tower S team is available. Please reach out to John Evans and Lee Byerly for any support. Contact Kashad Bowman on the Tower S team for any comments and questions about the SBC, and chat on the NWS chat room, Tower S. Now I believe it's time to facilitate some discussion. We seem to have some good questions here. So first question from Scott Lindstrom: how often is the detection algorithm updated with new data? For example, is all the data with ELSA used to recompute all the probabilities to generate a new algorithm? I guess another way of asking this is it easy to incorporate a couple of new months of data into the training? Sean, I guess that's one for me.
I would say so, yes.
Okay. Right. So there's a risk-benefit trade-off in updating with new cases as they come up. In machine learning, that's the term is online training, and that is, you just automate this cranked system that brings, like, as new data comes in, you update the model. The risks are way too high for us to do it in that case, because we have to really tend to the quality of the data before we commit to using it to training the model. Also, we don't want to be giving the users a new version of the model without giving them prior warning for it. So the way we've settled is on basically releasing a new version close to the start of the year instead, and doing some really targeted development to give it skill in particular things. And this clearly points out, the need to target some further skill in the outskirts of tropical cyclones. Okay, next question. The Aviation Weather Center, by the way, this is Steve Silverberg. The Aviation Weather Center sees a lot of turbulence PIREFs on the periphery of CBs, depending on the background flow, and also in anvil spokes, like you just showed. That's a comment that maybe, Sean, you can give some feedback on?
Yeah, that's definitely something we see at CWSUs as well. So yeah, we just, I guess that's where a product like this would certainly be useful, because it does show and highlight some of those areas pretty well.
Right. I'd say that that is a case, and this might come up in either stated questions or it is some of it is often the first thing that's brought up as a question or need for like more context in the product. So this product, one of the original motivations was, okay, you see these gravity waves all over this imagery that's produced by the ABI. How can we quantify that into turbulence probability? So we made this product, and it uses satellite imagery, and it uses model fields from the GFS, and it has developed quite a lot of skill, as you showed, with predicting turbulence at many levels of flight cruising altitude. However, one of the areas that still struggles the most with is turbulence around gravity waves. Although that is also a bit of a paradox. It has quite a bit of skill at estimating turbulence around gravity waves, because it usually says that there is no turbulence on gravity waves, and it's almost always right. Really extreme gravity waves with really big differences in brightness temperature, those tend to be, the algorithm tends to predict turbulence there, and it's definitely right. But then around, on the outskirts of convection, I mean, especially like far out where you see those spikes that Steve Silverberg alluded to, that's something that those are a bit of a rarity, where you see gravity waves like that actually are turbulent. And so that's something where we have to do some more research on. It's really important to point out that that's probably a case where when you look at the satellite imagery and you look at the product associated with it, it is probably underestimating the amount of turbulence there. Sorry for the long-winded answer to that. Okay, number 3. Apologies if this was stated, but are you guys getting an experimental feed of the product for AWIPS display? I think, Sean, you can field that one.
Yeah, we certainly are at ZDC, because I think, again, Steve Zubrick, our Science and Operations Officer at WFO Sterling, worked long and hard hours with Lee Byerly to try to get that feed into AWIPS, and it's actually been stable for many months. We haven't had any glitches or any blips recently. But again, that's at it only displays 36 to 37,000 foot layer, which that's still a pretty good approximation for en route and cruising altitude turbulence issues.
Correct. You see it sometimes where, in the breakdown of the 6 different layers, of about 2,000 feet increment. Occasionally you will see a sharp difference in what it says is the turbulence probability, but more often than not, those layers are there's a strong correlation between them. So to see what goes on in one layer in AWIPS, that tells you quite a bit. We have a comment here from AWC. They point out that they use the web version of this. And what would you say to that, Sean? Like, would you recommend complementing your view of this with the more extensive tools on the website? How does that experience between like being able to integrate in AWIPS compare to more tools on the web?
Well, I like both versions. I think there's some plans to maybe expand the package in AWIPS, but I can't really speak to that. I'll have to let the Tower S folks and the AWIPS folks talk about that, I guess, if they want to. But I like the way it's displayed in AWIPS. It's just a little different contouring. It's not really a contour even in AWIPS when you look at it. So it's a little bit better, or it's just a little different in AWIPS than it shows up on the web page. They both have good points. So I mean, I guess I'd recommend using both, honestly.
Okay. Yeah, that's a debate that is not close to being settled on over, should everything go in AWIPS, and then what happens when there's something out there that's not available from AWIPS. We have a comment from Lee here to Dan Lindsay. Dan, there's an experimental feed over the regional LDMs. We're happy to facilitate this for anyone interested. It includes the 36 to 37,000 foot turbulence prob layer. Quick question from Tim Schmidt. Are CONUS images also used in this product, or just the 10-minute full disk imagery? The answer to that is that it is just using the full disk 10-minute imagery. We have yet to find cases where we get temporal changes that even follow a 10-minute resolution in time. So for simplicity, we do it at full disk. Okay, next question. Is there any particular reason why a single 1,000 foot layer would be supplied for AWIPS display rather than the 30 to 41,000 foot maximum?
Yeah, that's a tough one.
Yes.
You could display it at 1,000 foot intervals, but there might be some processing issues with that. And I don't know that you get the I think 2,000 to 3,000 foot resolution is probably okay for cruising altitude, honestly.
Mm-hmm. Really, the best answer I could give is that the 30 to 41 large layer maximum, that came later. We committed to using one of the available 6 layers, and then later after that we did the maximum. And we're still working on the development of adding more layers, including these collective layers. Question number 6. Seems to be paraphrased. I'll make out what I can from it. The user is interested in the inputs and direct outputs of the machine learning model.
Yeah, that one's for you.
Yeah, definitely. The inputs are, you have 4 spatial layers: the GOES ABI water vapor channel, the 6.2 micron channel, the IR window, the high pass filter processing of the water vapor image. I won't get into that, but it looks at high frequency gradients, and then the topography. Those are the 4 spatial layers that we have, and then we also include mid to upper layer GFS, winds and temperature, and all of those. I won't get into the neural network architecture, but all of those get processed in a neural network architecture to produce the 6 layers of output, which are then trained against satellite, an archive of aircraft observations. That's the quick and dirty answer to that question. An anonymous writer says, thank you. I'm scrolling through the chat window now for other questions, but I think that tackles most of them. Sean, based on based on the feedback generally that we've gotten, is there anything you'd like to add?
No, I just would like to say thank you for producing the product and letting us use it experimentally and putting it on the internet for all to use. It looks like it's a very good product, and I'm actually kind of amazed that it predicts any turbulence at all, considering that PIREPs, and particularly turbulence reports, are so subjective.
Yeah. Hey, it's an honor and a privilege to be able to do research like this. And yeah, it looks like we have this in common, that it's quite a motivating force to see like this new technology really deliver, right?
Exactly, yes.
And yeah, it really gets you interested in, what, if we were able to make such a leap with one sort of innovation like that, then can we do it again and again? And yeah, we have about 2 years of support left to do exactly that. And so, yeah, user feedback is critically important. We could just keep tweaking the knobs, to get that skill number going up and up a little more each time. But usually that doesn't really target what the users want the most. There's much more of a qualitative nature to this. For example, if you want especially to know, I see these gravity waves here, tell me for sure what I can, what kind of meaning I can draw from that. That's a different question than just improving the general skill in a machine learning framework. That requires much more targeted development. But really, you summarized the main issues with where you need improvements in the operational settings, and we take that very seriously.
Thank you.
Yeah. Also, Sarah Griffin has not been mentioned in this, and she definitely deserves a great deal of credit in this. She is she does a lot of development on this too, and she is the one who produced the web, the entire web interface to this, and gets you and gets the website in shape to really address the biggest needs that the users have. So yeah, so that's great for the team effort. And Lee Krantz is the AWIPS liaison for this, and he's the one who's been able to bring this into AWIPS. Tim Schmidt has a note here on the chat window. When we talked about turbulence from ABI GOES 20 years ago, there were a lot of eye rolls. I have no doubt. And especially if somebody has a lot of familiarity, or had a lot of familiarity back then about a lot of false promises that were made about what could, what kind of turbulence you could quote unquote see with the GOES imagery. You're in for a lot of disappointment. There are cases where, yeah, you could show cases where something weird happened, and then and there was a feature in GOES for that, but you couldn't generalize it very well. And so, yeah, we've come a long way, and it's very gratifying. Okay. So I get the sense that this has wrapped up, and I think let me look over the facilitator notes again.
Thanks, Tony. I can take it from here if that's all right.
Great.
All right.
Thanks.
Say again.
Sorry, I just wanted to thank Tony for facilitating, and obviously for generating the product. I think it's a really good example of what machine learning can do for National Weather Service products, or for meteorological products in general, honestly, at this point.
Yeah, absolutely. Thank you, Tony, and your team, as you pointed out, for all of your and their work on this and getting this in front of forecasters. It has been something that's been useful in an area where we don't have very many, or we didn't previously have very many observations. So this is starting to shed some light on a very important area. Sean, of course, thank you so much for telling us the story of the ZDC airspace and how your operations work with this product. Washington Air Route Traffic Control Center, really appreciate that. And thanks to both of you for being here today for this Satellite Book Club seminar. We hope you'll join us next week, Thursday, August 19th, again at 12 noon Eastern Time. Dr. Katie Crandall-Vigil from CIMSS with 2 M's and the NWSOPG, talking about color vision deficiency and interpreting satellite RGBs. So I hope you'll join us again next week. Until then, please get in touch with our Tower S team if you have any questions about the AWIPS configuration for this or other satellite products. Stay well, and see you then. Bye-bye.